And here we are back with the second part of our lecture on subsets, set operations, and Venn diagrams. We're going to talk a little bit more about some set operations, but they're going to tie very closely with Venn diagrams. We'll see those as well. And yeah, let's just jump right into it. So remember we talked about sets, and we talked about how we can talk about like subsets, sort of how they can be related to each other. Now we're going to talk about how sets can interact with each other to create another set. So let's talk about an intersection here. So let's say I give you two sets, A and B, and I then ask you, hey, what's the intersection of those? Well, the intersection of those sets is every element that's in both of them, okay? You can see that down here. I say, hey, X such that X is in A and X is in B. So the elements that I'm talking about, they have to be in both A and B. And this results in another set, obviously. Let me show a quick example here. I didn't need that page. I have one right here. Let's look at this example. I'll jump back to the definition. The intersection of these two sets. Well, let's just look pretty vaguely. There's the 6s and there's the 4. Those are the elements that are in both of these. 1 and 9 and 2 and 3. Those don't appear in both sets. So 4 and 6 are the ones that appear. So what I'd say is that my resulting set is A intersect B. It's sort of this upside down U looking thing. We actually call it a cap. Let me write that there. Cap. And this set is equal to the set 4, 6. So when I take these two sets, A and B, and I intersect them, I get another set. It's the set 4, 4, and 6. Right here. We call that A cap B or A intersect B. You'll probably hear me say more often than not. So that intersection set right there, we've got this definition. Again, just because this is confusing, I don't want to get a lot of practice with it. Let me step through this and say it verbally as I go through. A intersect B. This is a set. I'm calling it A intersect B, and that set is equal to all of the objects, all of the elements that I'm temporarily going to denote with an X. They're all of the elements such that they're in A and they're in B, right? So it's everything that's in A and in B. That's intersection. We see this example right here. We got 4 and 6. Boom. And actually, before I go into another example, let me draw a little Venn diagram here. If I've got these two sets, the intersection is going to be that guy right there, right? That's just everything that's in both of them. Sweet. Let's do another example. Intersection of two sets. So I've got the natural numbers, and I've got the even natural numbers. So we want to be careful with these dots here. There's an infinite number of elements in these sets. So when we talk about the intersection, we gotta be a little careful here. Let's look. Which things are in both sets? Is 1 in both sets? Yeah, it doesn't look like it. It's not even, so it's not in that even natural numbers. So is 2? Yeah, 2's in both. 2's right there. That's good. What about 3? No, 3's not in both. 4? Yep. What about 6? 6 actually is. I didn't write it, but there's that dot. 6 would sort of be right there. And they go on. They keep going on, right? So then 8 is as well. So is 10. And it actually turns out all of these even numbers, the entire set here, is contained within the natural numbers. And that makes sense, right? I mean, heck, it's called the even natural numbers for a reason. They're all natural numbers, and then it's just the ones that are even. So in this case, the intersection of N and E, N intersect E, It's actually just E, right? And let me write it this way. Let's write out the numbers. It's 2, 4, 6, 8, 10, and it keeps going on forever. But this is just E, right? So this is an interesting case where I actually have my set out here, and I have a set that's just contained within it. And so the intersection is exactly just that set right there. Awesome. So let's go ahead and do something related to intersection, but it's kind of like the opposite a little bit. And we'll talk about union. So if I have two sets, A and B, the union is every element that's in either of them, okay? And so if I have two sets, I just basically look at each of them and I just write down everything. That's pretty much all we're doing, because I'm looking at the elements that are in A or they're in B. So as long as they're in either of them, they're in the union. This should be a lot more straightforward. Let's do an example here. So if I have A and B, I'm using those same sets that I did before. I've got the union A, union B, and this symbol here. This is the union symbol. We'll call it a cup sometimes. You'll hear most people just say union. It's every element that's in both of them. Well, or excuse me, that's in either of them. So 1, yeah, that's in either of them. It's in A, that's fine. 2, yeah, that's in B. It's not in A, but that's okay because it's in B. So as long as it's in either of them, then we're good. 3, yeah, that's good. 4 is in both. So here's a question. Should I write it down twice? And the answer is no. We tend not to, we don't want to repeat ourselves when we're writing sets. So you wouldn't write 2 4s. That's bad. Don't do that. Then 6, that's in both of them, but we'll just write it once. 9, it's not in B, but that's fine because it's in A, so it's in the union. So this union is everything that's in either set, right? It's kind of just take all the numbers and write them down and then erase your duplicates. You know, don't have any duplicates in there. Venn diagram wise, this would actually look like everything that's it's in A, or it's all the stuff that's in B, right? These elements only have to be in one or the other. Let me move that there. There we go. They only have to be in one or the other. So in fact, all of the blue and all of the orange, all of that, everything I've colored, everything I've filled in, that's the union in the sort of a Venn diagram sense, right? And so that's union and intersection. You can see very clearly the difference in the Venn diagrams. This union, it covers the whole Venn diagram, both circles completely. And the intersection is just that inner part, just that overlapping part, right? That part here that's shaded in blue and orange. And we'll actually get more into using the words and or in a rigorous sense. That'll be sort of the next section of, or the next topic, section of topics that we'll talk about. So let's continue on. Let's find the union of these two sets. Well, remember here, this was that example where E was contained solely in N. So the union is everything that's in E or everything that's in N, right? And so it's everything that's shaded, which is just N, right? And you can see this. I could write down everything that's in either N or E. So let's go, well, 1, yeah, that's in either N or E, it's in N. 2 is in both, that's cool. I don't really care now, but it's in both. It's in at least one of them. 3, yeah, it's in N. 4, in both, but I don't really care. It's at least in one of them. 5 is in N, and this just keeps going. 7 is in N. I didn't write it, but it's, yeah, because I wrote the ... but it's there. And so this is just everything. This is just n, right? So this is another sort of interesting case here. Now, here's what we want to, here's the next thing that we want to do. We want to talk about cardinality, right? Remember we talked about that last time. We talked about the number of elements in a set. And it actually turns out that the number of elements in a union is related to the number of elements in an intersection. This formula looks very ugly and complicated. Let me come back to this. I want to do an example first just so you guys can see. And let's actually come here. So we had this example with 1, 4, 6, and 9, and 2, 3, 4, and 6. And you'll notice that after I do the union, I end up with 1, 2, 3, 4, 5, 6 elements in the union. And so the question you might ask is, how the heck did I get that from these two sets A and B? And here's exactly how I got to that 6. What I did was I said, hey, there's 4 here, and there's 4 here. So what I'm going to do is I'm going to add those. And that's going to give me an 8, right? And then what I'm going to do is I'm going to subtract off the number of elements that are common between them, aka the number of elements in the intersection. Remember, we saw that intersection back here, 4 and 6. There were 2. So I'm going to subtract off that 2, and that's going to give me my 6. And that's exactly how I can get this sort of a formula on how I can do this, right? How I can figure out how many elements there are, right? So let's go ahead. Let's do another example here. So and then I'll come back to this formula. Let's say I've got 42 students that are taking math. So 42. Well, let's just say math equals 42. Let's say I've got 51 taking English. And then 12 are taking both. So if I walked into this math class and I counted the heads, there'd be 42 of them. If I walked into the English class and I counted the heads, there'd be 51 of them. But some of those students are in both, right? And in fact, there's 12 of them. And so if I say, okay, how many students are in either a math class or they're in an English class? I don't want to know about, you know, which ones or how many are in both or things like that. Basically, I'm just asking you, how many students are there? How many people are there? Then you might naively think, hey, let's just add 42 and 51 because that gives me the number of people. Well, but if some of those people are the same, you're double counting them. And you'll hear me use that phrase a lot. I'll say double counting quite a bit. That's bad. We don't want to double count someone because we just want to know exactly how many people there are. So while you might naively do 42 plus 51, giving us 93, that's not the number of people that are there because 12 of those people were in both of them and you've double counted them. So what you want to do is you want to subtract off this 12. You've counted 12 people an extra time, so subtract off 12 from your count, and you're going to end up with 81. And that's going to be the number of people that there are. That's the number of people that are in either math or they're in English. And so what I've done here, you can see formula-wise, I've added the numbers that were in math and English, and then I've subtracted off the people that were in the intersection of math and English. They were in both. And that's what this formula back here says. To get the number of people, the number of elements in the union, I take the number of elements in A, the number of elements in B, I add them, and then I subtract off the double counters. The elements that I've counted twice. That's the elements in the intersection. They've been counted 2 times. So I subtract off just one of those double countings. And you can see that here. Did that work? 42 plus 51 minus the 12. I could flip this around and I could actually ask you for, here, let me pop back here. I could ask you for this. I could ask you for the number of people in the intersection. You can do some algebra you know, flipping things and, you know, bringing things over to other sides. I could ask you for the intersection and give you these three. I could ask you for A, number of people in A, and give you these three. I could ask you for B and give you these three. There's a whole lot of things I could do there. All right, next thing we're going to talk about is set subtraction. And so this one can be complicated. We say set subtraction is definitionally, we call it the difference of two sets. So if I have two sets A and B, the difference A minus B is the set of elements that are in A, but they're not in B. And so what we've got here, notationally, A minus B, that's that difference, is equal to the set of elements X such that X is in A and X can't be in B. So it's in A, but it's not in B. Now let me be very clear. That's very different from B minus A. A minus B and B minus A are very different things, because B minus A would be the set of elements that are in B, but not in A. And let me do an example just to show you how these are actually different here. So I've got A and B, again, using these same sets that we've seen before, 1, 4, 6, and 9, and 2, 3, 4, and 6. Let's do the subtraction A minus B. And I'll pop back here again, just to this definition real quick. Two sets A and B, it's the things that are, the difference between them is the things that are in A, but not in B. So here's what we do. Which things in here are in A and not in B? Well, 1, let's go ahead and look at 1. That's in A. Is it in B? No. So that's good, right? I've got my A minus B. She'll put that in there because it's in A, but it's not in B. 4, how about that? No, that's in B, so I don't want that. Let's get rid of it. 6, yeah, that's in B. I don't want that. Let's get rid of it. 9, is that in B? No. So there's your set subtraction, A minus B. Let's go ahead and do this now, though. Let's do B minus A. So this is the elements that are in B, but not in A. So 2, let's look at that. Is that in A? No, but it's in B, so let's put it there. 3, is that in A? No, it's not in A, but it is in B, so we put it in there. 4, yeah, that's in A, it's right there, so I get rid of it. 6, yeah, that's in A, it's right there, so I get rid of it. And so we're just left with 2 and 3. You can kind of think about the subtraction as just like canceling off this, like I just scratched out the 4 and the 6 there. You could do that. You can look, if you're doing B minus A, you can look at B and just subtract things from it as you see them in A. That works for A minus B as well, depending on however you want to think about it. But there you go. And this very clearly shows that these two things are not the same, A minus B and B minus A. Let's go ahead and do another example. Let's do N minus E first. So N minus E, we're looking at things that are in N, but not in E. So let's go through. 1, is that in N? Yes, obviously, because that's what I'm looking at. Is it in E? No, it's not in E. So I better put it in N minus E. 2, that's in N, obviously, because that's where I'm looking. Is it in E? Yeah, it's right there, so I cross it out. Keep going down. 3, well, it's in N, but it's not in E, so I put it in my subtraction, in my difference. 4, yeah, it's right there, so I get rid of it. 5, and I just keep going. 5 goes there. 7 goes there. 6 goes away. 8 goes away. 9, 10 goes away. 11, and it just keeps going on and on and on. This is all the odds. It's all the odd natural numbers. Let's do another example. E minus N. Everything that's in E, but not in N. Well, if you look at this, everything that's in E is in N, right? Look at the 2, the 4, the 6, the 8, the 10. All of those occur in this natural numbers. So in fact, there's actually nothing here. It's just an empty set. Remember, we can denote that by that sort of circle with a line through it. That's the empty set right there. And there you go. There's another good example for you. One last thing I want to do with subtraction and differences is just show you just an alternate way to think about this with Venn diagrams. If I do the difference A minus B, what I'm looking at is I am looking at things that are in A, but they're not in B. And so everything that's in A is in the red circle. Everything that's in B is in the green circle. So if I want the things that are in A that are not in B, then I'm just looking at things here in this sort of moon-shaped part. It's just this section right here, because those are things that are in. Those are the things that are in A, but they're not in B. And so what you can actually say is that A minus B is the same thing as A minus A intersect B. You're probably not going to like use this as a formula. I just like to show it just sort of pictorially, just for you guys to see. But that's basically what you're doing, is you're taking the things that are in both of them and you're just removing them from A, right? Obviously, B minus A would be the opposite. B minus A would be over here, that guy. Great, there's subtraction. One last thing I want to mention, De Morgan's laws. These are kind of more optional. You don't have to use these. These have to do with complements and unions and intersections. And there's ways you could prove this. I'm not going to emphasize these too much when we talk about sets. I'll emphasize them a little more when we do logic and truth tables. But if I have A union B and I complement that, remember we talked about complement being the things that aren't in it, things that are in the universe, but they're not in that set. So if I take the set A union B and I complement it, then I end up with A complement intersect B complement. Those are equivalent sets. They are actually equal sets. Remember those definitions of equal and equivalent. Again, I almost just flipped them right there. These are equal sets. They're the same exact thing. And then likewise, A intersect B. If I take that and I complement it, that's the same as A complement union B complement. So what you can see is it's kind of like I'm distributing this complement sign and I'm flipping the union to an intersection and intersection to union and vice versa. These are called De Morgan's laws. You're welcome to use them if you want. You don't have to. There you go. That's actually it on the subsets and set operations and Venn diagrams. And you'll have some good worksheets to work on. And I'll leave that to you guys and we'll finish up this recording here.